So hello guys, welcome back to my channel. Let's discuss the Leetcode weekly contest 478. We'll discuss the first three problems. So this is the first problem. You are given an integer array nums of length n and an integer k. An element in nums is said to be qualified if there exist at least k elements in the array that are strictly greater than it. Return an integer denoting the total number of qualified elements in nums. So basically what they are trying to say is, what is the definition of this qualified element? So let's read the sentence again. Element in nums is said to be qualified if there exist at least k elements in the array that are strictly greater than it. Okay, so if I have some element x, let's say. So basically what this problem is trying to say here is, this is this integer is qualified. This integer is qualified if I have k more elements which are strictly greater than this. Okay, so if I have something like x plus 1, x plus 2, so if I have something x plus k minus 1, so if I have some integers like this, now these could vary, they can be very random, like x plus y, x plus z, something like that. So if I have k integers, then we can conclude that this is a qualified element. So to visualize this properly, let's take a example. Let me just erase this. So let's take an example. 1 2 3 4 5 6 7, and then k equals to 3. So now for 1, we see how many elements are strictly greater than 1. So we see there are 6 elements, which are 2 3 4 5 6 7. 6 elements are greater than 1. So is 6 greater than equals to k? Yeah, we have 6 elements which are greater than 1, and so what we need to do is, this will actually be a qualified element, because what the problem is saying, we need to find the elements which are strictly greater than this, and then if the count of those elements is greater than equals to k, then it is a strict, or it is a qualified element, otherwise it is not. So it has so it is saying it is saying at least k elements in the array that are strictly greater than it. So it says there should be at least 3 elements in the array that are strictly greater than 1. So we have 6 elements which is greater than k, so this is a qualified element. Similarly, if it's C for 2, we have 5 elements which are greater than this, right? And we need at least 3. So 5 is greater than 3, so this will also act as a qualified element. Now as for 3, we see that we have 4 elements which are greater than 3, right? So we need at least 3 elements. We have 4 elements, so this will also contribute to our qualified element. We have a 4 here, and now we check how many elements more do we have greater than 4. So we have 3 and we need at least 3. So do we have 3? Yeah, we have 3. So we mark it as qualified as, right? Now if we go to 5, we only have 2 elements left and we need at least 3. So this will not act as a qualified element. This will also not act as a qualified element, and this will also not as a qualified element, right? And now you can see this function is monotonic, meaning if one integer fails, all the elements after that will automatically fail, because if let's say x is not a qualified element, so that means the number after x are not greater than equals to k, right? So this count is actually lesser than k if it is not a x is not a qualified element. So all the elements after it will also have count lesser than k, right? So this will never be true again. We can say that, right? So basically what we can do is, the order of elements here does not matter, right? So we can sort the array. Let's take another test case. So we have 1 1 2 2 and 3. Okay, so now we are checking for 1. we find we have to take the elements which are strictly greater than this. So we first sort the array, and then we take the upper bound of this one. Like we need to find the first position which is just greater than 1. So this is this one. 2 is strictly greater than 1, and this is the first time it is occurring. Let me write the indices as well. And n equals to 5, right? Because there are 5 elements in the array. Now we can see that from this element starting onwards to all the to the end, we can take all the elements, right? From 2 to 4 we can take all the elements. So basically if we do a n minus idx, if this is an idx, we'll get the count of elements which are strictly greater than 1. Okay, and now if that is strictly, we can take this as count, and if a count is strictly or not strictly, if greater than equals to k, then we can increase the result by 1, meaning this will act as a qualified element, right? So we can just binary search by first sorting. So let me again take this example 1 1 2 2 3, and so I binary search the upper bound of this, the element which is just greater than 1, the first position of that, which is 2, right? We can take, now we know we can take from 2 to the end of the array. We have 5 elements, and the indexing goes like that. So if we do a n minus I, we'll get the count of elements which are strictly greater than this, or not I, this is idx. We'll get how many elements are greater than 1, right? And then if this count is greater than, if count is greater than equals to k, that means this can act as a qualified element. So we can just take this and increase the result by 1, and then we can look for this one, right? So this is what basically we are trying to do here. We first sort the array, we maintain a count, now we find the index. So basically we have this upper bound function in C++ by default, which will find the upper bound of nums of I, and this converts it to the index. Similarly you can look for Java one, or you can write your own binary search logic here, and n minus idx will actually give the total number of count. If that count is greater than equals to k, we increment the count by 1, or increment the result by 1. What I can say, this is result, right? So this is basically count of elements which are strictly greater than the current element. If this is greater than equals to k, then we can increase the result by 1, and then we can just return the result, right? So I hope it is clear. Let's move on to the next problem. I'm sorry. So you're given a string s consisting of lowercase English characters. Return an integer denoting the maximum number of substrings you can split s into, such that each substring starts with a distinct character. That is, no two strings start with the same character. So we need to do what we need to do in this problem is we need to maximize the number of substrings I could possibly split that. So this is let's call this a string s, and maybe these are the characters of string s. So we need to maximize the substring taken in this string. We need to take as many substring as possible, and there's one condition, that every substring with should start from a different character, right? So this s1 has to be different, s3 has to be different, this one has to be different, sn has to be different. So all the first characters of the substring has to be different. So all the first character of the substring has to be different, right? So basically if you have a string like this, a b b c d e and g g, let's say, so basically we start iterating from here. We encounter a, and maybe this is our set, let's call that a set. So do we have a in our set? No, we do not. Also let's maintain a result over here, right? So do we have a in our set? We do not. So we increment the result by 1 and we start taking this substring, right? We encounter a and we can see that it is present in our set. We just encountered it. So we do not increase the result because we can just take that into our first string as only. And then we encounter this b. Do we have a b in our set? We do not. So we insert a b here and increment the rest by 1 because we start taking the next string. So we start taking the substring from here, the second substring. Now we again encounter a b. We check that if it is present in s, it is indeed. So result remains as it is. And now we move on to c. C is not present inside s, so we increment the result again and we start taking next substring from here, right? And we insert that into s. Similarly, if there is a d, d is not present inside d here in the set as well, so we increment the result again. This can be broken down into again a substring. Now e is not present, right? So we can insert a e here, increment the result. We can move on to g. G is not present, so we insert g, we increment this. Now we encounter g. We can see that g is present, right? So basically we do not need to increment the result because it is already present. If we for example encounter a ab again, so let's say we move on to here. So we encounter a and we can see that a is already present inside here, right? So basically we were taking this substring and a was already present inside this set, right? So we need to include that in this substring only. We cannot begin a new substring from here because this was already taken here, right? This a was actually taken here, so we cannot begin a new substring from here. Basically what the question says, uh, each substring, if you will see here, each substring must begin with a distinct character, right? So we cannot, you know, start a substring from here. So we expand this substring to here. We check for b is also present, so we expand this substring to here, right? So this, now the substrings get divided like a, bb, c, d, e, then gg, aab. So we have substring a, bb, c, d, e, g, g, a, b. So these are the substrings that we have. And so don't you guys agree that the number of unique characters in the string will be our total answer? Because the substring can be of size 1 also, right? So the number of unique characters, if we had something like a, b, c, d, e, f, we can just take a, b, c, d, e, f separately, a one size substring, and then that would give us the answer, right? So we can just count the number of distinct characters in this string, and then that would be our final answer, right? Because let's say if we have a, b, c, d, and so we have 4 distinct characters now, so we can take 4 strings here, 4 substrings, or and if we encounter again abc and abc again, so we can we know that we have already taken this inside the set, so we can just expand this last substring to the end, and this will cover everything. And if we encounter another, let's say a z, so we can begin a new substring from here, right? So we can basically just count the number of distinct characters. We can do that by maintaining a set, right? So I just coded that fast in the contest. You can just ignore this. We can iterate from 0 to n, n minus 1 index, and then we can insert all the characters inside the set, and then we know the set only stores the distinct elements, and so this will store only the distinct characters. And now we can just take the size of that will actually give me how many distinct characters do I have, right? So I hope it makes sense. Let's move on to the next problem. Yeah. So let's read this. Minimum absolute difference between mirror pairs. So a mirror pair is a pair of indices a and j such that 0 is less than equals to I is less than j is less than nums dot length, and reverse of nums of I equals to nums of j, where reverse of x denotes the integer formed by reversing the digits of x. Leading zeros are omitted after reversing. For example, reverse of 120 equals to 20, 21. Okay. Return the minimum absolute distance between the indices of any mirror pair. The absolute distance between indices I and j is absolute 1 I minus j. Okay. So this is a lot for a problem. I'm sorry. Let me try to break this down. Basically, let's take the first sample, 12, 21. So I could take 12, 21, 45, 33 and 54. What they're telling here is a mirror pair is a set of indices of I and j where I has to be lesser than j, so these have to be distinct indices such that nums of I or reverse of nums of I equals to nums of j. So basically what this reverse means is when I write let's say this is a number 312, so when I write this in reverse order, so this was 312, if I write it like this 213, this is its reverse form, right? So basically that is what the question is saying. If we had a 3120, that is what they're saying ki leading zeros are omitted, so we leave this leading because after reversing this will be 0213 and we can just remove these leading zeros, so this becomes 213 here. And so this is a mirror pair here, right? These elements have to be distinct and the reverse of nums I has to be nums of j, right? Okay. And basically at last what we need to do is return the minimum absolute distance between the indices. Okay, so the absolute distance between indices I and j is basically I minus j. This is the absolute distance and we need to minimize this as much as possible. So basically let's take this sample. If you have a 12, the reverse of 12 will be 21, right, which is here. So we need to find the 21 closest to this 12, right? Then only this result will be minimized. Do you guys agree that if we are trying to minimize, if let's say this is I and this is j, then do you guys agree that the closer the I and j are, the lesser is our answer, right? Let me try to break that down for you. So if we had a 45, 1, 2, 3 and then a 54, so the reverse of 45 is what? 54. So we need to find the occurrence of 54 which is closest to 55 just after the 45 one, right? So we need to find the closest one to the 45, and if we find the closest one we can just take this and then we can take the absolute distance of this, right? And we can maintain our answer here and we can just take the minimum of all such pairs whose reverse exists. So for the pairs whose reverse do not exist, like 1 is a mirror of itself, 2 is a mirror of itself, or no, let's say 1 is a reverse of itself, 2 is a reverse of itself as well, and all the single digit elements are a reverse of itself. So basically we can do nothing about this because I and j are same in this case. I and j both are same, right? So we cannot do anything for these cases, and so we'll leave them as it is. If we even had something like, let's say 45, 1, 2, 3, then maybe 12 and then a 54, So you'll see that reverse for all these elements do not exist. The reverse only exists for 45, which is 54, which is here, and we need to find the closest 54 to this 45, right? I'm sorry, I'm having a little cold there. So basically we need to find the closest 54, closest one to the 45, right? And we'll do for all such pairs whose reverse exists. So first of all, we'll create a map mapping all the reverse value to this one, right? So let's say I have a 45, so I'll map it with its reverse form, which is 54, right? I'll create one, I'll take one, and I'll create its reverse form, which is 1 only. For 2 this is 2 only, for 3 this is 3 only, and for 12 this is 21. Let me write that down here. Let's say here. For 12 the reverse is 21, and for 54 the reverse is 45. So we stored the reverses of all the elements in the array. We can do this in log base 10 of AI, because there are at max log base 10 digits. Basically the length of the digits is log base 10, because we are using the base 10 format here. Or we can see that, I'm sorry, in the constraints the nums of I would go from 1 to 1e9. That would mean that it can have at max 10 digits, right? It will only have 10 digits. If we write something like this, 1 2 3 4 5 6 7 8 9, so this will have 10 digits, right? And so 10 is not a very big number, right? So we can just reverse that in, let's say, constant time. This is almost constant. 10 is constant for every number. We can reverse that and store the reverse pair in a map, right? And now what I can do is I'll start iterating from here 45, then I'll check what is the reverse of 45. So I'll check inside this map what is the reverse of 45. So it is actually 54. So I'll look for the position of 54 which is nearest to 45. So this is the position of 54 which is nearest to 45. So I'll call this j and I'll call this I, and I'll maintain a minimum as well, right? This would be infinity for now, int max or say. Now let me write the indices here as well. So z or 0 1 2 3 4 5. So j minus I in this case would be 5. So minimum would become 5, right? And now we'll move on to the next one, right? Now this is our I. Okay. Now we find the reverse element of this, which is the element itself, and now we'll see I and j, which is also present here. So there's no gap between those elements. This is the same element as reverse of itself, so we'll not take this. We'll move on to the next one. 2 is the reverse of itself, and the position is right here only, right? So I and j again are same at one position. We'll go here. Similarly for this one also, this is a one digit number, the reverse and the element are equal, so we'll go to 12. Now we see the reverse of 12 is 21, but 21 is not present anywhere, so we do not try to do anything. We'll just try to move on to 54, right? The reverse of 54 is 45. We have that in the array, but we need a 45 which is actually ahead of this or to the right of this, right? If we had a 45 to the left of it, wouldn't you agree that we would have already taken this? So if we say the reverse of this is 45, right, and it exists on the left side of it, so do you agree the reverse of 45 54, which is the current element? So we would have already taken this into account, right? So we would have already taken it if it would have been present on the left. So what we try to do here is If it is present, if the index is actually lesser than the current element, let's call this I. If the j is actually lesser, so we erase this and we search for the next one, and next for this one do not exist, right? And so we do not take anything for this, and the answer returned here is 5 now. If the answer continued to remain infinity, then we would have returned a -1. As the question says, if there is no mirror pair, then return -1, right? So basically I could first create a map of an element with its reverse form, then I could create a map of an integer and a set. That is what clicked to me in the concept, in the contest. So basically I can go through all the elements in the array, and I could store all the positions, you know, of that in the set, of the elements in the set. So basically I have a 45 here, 1 2 3, a 12 here, and a 54 here. Okay. Now the position of this is 2 1 2 3 4 5. These are the positions. So basically now I'll create a map of positions. 45 will have a 0 here, right? 1 will have a 1 here. 2 is present on the position 2. 3 is present on the position 3. 12 is present on a position 4, and 54 is present on a position 5. Let's say there was another 54 and a 45 here as well. So this is 6, this is 7. So there is a 45 present in 0 and a 7. So I'll take this here, right? And a 54 is present on 5th index and 6th index. So I'll do this. So now we have created a map of all the elements, and they map to its corresponding indices. Now we start iterating from the first element. Let's say I'll write the array elements here: 1 2 3 12 54 54 and 45. So now I'm on here. This is our I. When we reverse this, we see 54. We go to this particular set, then we check the first position. The first position of the set will be the closest position to I, and we can see that. Let me write the indices here as well: 4 5 6 7. So we can see that 5th position of 54, the reverse of I, or reverse of nums of I, is closest to this position of 45. So we take this into account. The minimum for now is infinity. Minimum is infinity, right? So we take this into account. We make a pair out of this. This is our j. This becomes our j, and 5 minus 0 is 5. So this becomes 5. And now we move on to this one. Now as we see, I and j both are same for this one. We'll move here. We'll move here. Then we'll move here. The reverse of 12 is 21, which is not present in the array, right? So we'll move to 54. Let's move this. Now we have moved to 54. This is our I. Now reverse of 54 would be 45, which is present inside our array, right? So we check the first element of the set. Is it strictly greater than the current element? Which is not, right? So we remove this from the set, and then we look for the next element if there is any. So there is a next element indeed, which is present in the 7th position. So we can determine that this is the closest position to 54. This becomes our j, and now we take 5 and 7 and take this into account. So 7 minus 5 is 2, right? If we take this into account, 7 minus 5 is 2. So minimum now becomes 2, right? And now we get to this 54. This becomes our I. Let's move this. This becomes our I. When we encounter 54, when we reverse it, this becomes 45, and I check the index of the beginning of the set. So this is 7 again. We have removed this from the set, right? So this is a permanent change also, right? So the 45 is present at the 7th index, which is strictly greater than 6, which means it is coming to the right of it, and 7 is actually quite closer to 6. the difference of 7 minus 6 would be 1. So it is actually quite closer to this one. So we can indeed take 1 here, and the minimum would become 1 here, right? We need to take minimum of all such cases, right? Return the minimum absolute distance between the indices of any pair. So we are taking the minimum out of all such possibilities. Sorry. So now this becomes this gives us a minimum distance of 1, because this becomes j, and 7 minus 6 is just 1. So now we move on to here 45, right? So 45, reverse of 45 is 54, and now the current I is 7, but you see that j, the 54 which is present to the left of it, has already been taken into accounted for. We just took this 54 and 45 here, right, when we took this 2. So we can remove this from the set, and we can check the next element. Is it strictly greater than the current element, which it's not. So we have already taken this into account as well. We remove it and we check for the next element. Currently there is no element left, so we cannot take anything for this one, and we leave the minimum as it is, and we return out of the loop, and this is our answer 1. So that is pretty much for the problem. This is just an implementation problem. I'm making if you see carefully here, if you see carefully here, I'm making at most n changes, right? I'm iterating over all the elements, then I'm iterating over the set. So this is basically n log n. The time complexity is n log n, nothing more than that, right? Because essentially I'm iterating over the indices, and then I'm removing it, right? So I'm not taking this permanently, taking this 0 permanently here, or taking this 5 6 permanently here. So I do not need to check from the starting again and again and again key this exists or not, this exists or not. I've taken this, I've removed this from the set, and now this set becomes empty, right? This has nothing. And similarly 45, this 0 gets removed completely, because we see for this element which is at 7th position, if some elements in the set are cannot be used for 7th element, how can they be used for 8th element, right? If there is an 8th element, how can they be used for that? Because 8 is greater than 7, and if some element which cannot be used for 7, then it is for sure that it cannot be used for 8 as well. It is a concept like a monotonic stack, right? So we basically erase that from the set, and then we can move on. So basically I can have at most n removals if I add these values again, 1 2 3 and 12 again. So we'll have these removals as well, right? So we'll have n removals, which costs us log n time, because inserting and deleting from a set is log n. So the total time complexity would be order of n log n. Space complexity would be order of n, because we are taking all the elements and mapping it to its position. So we have unique elements into the number of time they occur. So this is essentially total number of elements in the array, right? So this is it for the problem. This is the code for this. I'm basically first trying to map the current element to its reverse pair because we need to get the reverse in O of 1. So we can do that in log base 10 and log base 10 AI, I'm sorry. So we are doing this here. Then we create this position map, and we insert the positions of nums of I2 here, and then we start iterating from the current element. This is our reverse form. We'll get the reverse of this, and we'll create a vector, temporary vector. I'm creating a temporary vector here. Then I start iterating over the this map. So position of rev, this is the reverse form, and the position of this will have to start iterating from I'm actually iterating over the set. I'm actually iterating over this set, right? So if the value of set, the current value of set is actually greater than equals to I or less than equals to I. That means I would have already taken this into account, so let's push that into temp variable. Otherwise, if it is greater than I, then I need the one that is just greater than I, the lowest one which is greater than I. So I just break out of this loop, and so I'm adding all the elements that I want to remove inside a temp, because I cannot make live changes here because I'm iterating over the set, right? This is just specific to C++. Java users can probably skip this. And now I'm iterating over the temp and removing these elements from the position of rev, that is reverse. This is the reverse of original one, and these are the position, and I can just erase the elements which are not useful anymore. And after doing this operation, if this set is still not empty, then I could just take the first element. Dot begin gives the first element, and then I could take the difference between them, and I could take the minimum of all such cases and just return from here. So this is pretty much it for the third problem. I hope you got the solutions. If there are any doubts, you can probably ask me in the comment section. I'll be more than happy to help. Baki, I couldn't solve the fourth problem, although I know it is of segment tree. I tried solving it, but I couldn't actually solve this one. So yeah guys, that's pretty much it for today. I'll see you tomorrow.